Welcome to our second lesson on magnetic effect of electric current. In my previous lesson, we looked at an experiment which we explained using a compass and wires. The wires were connected to the cell so that we can have current flowing in a wire, and we saw the effect on the compass. We didn't have magnet per se, but we were able to observe the effect on the pointer. The pointer, remember, from magnetism can only be affected by a magnet. So you bring a magnet near the compass, the pointer is affected. It deflects. So today we are going to continue. This is lesson 2. We are going to see the magnetic effect of a current carrying conductor which is straight. So you have a straight wire. An example here, you have a straight wire like this is a current carrying conductor, okay? This. And then you sprinkle iron filings. The end of the wire are connected to the cell. So these two ends, 1 and 2, they will be connected to a cell. When we connect this wire to the cell, the current will flow depending on the positive and the negative of the cell. Okay? So for illustration, let us imagine the current is flowing up. So the current is coming, flowing up, goes, comes again, flows up. When we observe the iron filings, we find that they have formed patterns. Okay? So observation, iron filings form patterns. Those patterns are in concentric shapes. They are like a small circle, another slightly big, another big, and so on. It's like different circles with different radii. Okay? So a small one begins, the next one is slightly bigger, and then big, bigger, biggest, and so on. So those shapes look like this, concentric circle. This is a conductor. So we are saying that the current is coming down here, going up. The patterns represent the magnetic field lines of force. Force is a vector quantity, and therefore it must have size and direction. At this level, we are not considering size, but we are considering direction. Okay? So these are the kind of patterns, concentric circles. Now, the issue is, since they must have a direction, how can one tell about a direction? So we said that you can use Fleming right hand grip rule. Grip, to grip. So let us say this is the direction of current, up, and this is the conductor. So when I hold, you can see the fingers, they are curling like that. This is the direction of current. direction. Then if I want to know the direction on those concentric circles, I will use the curling fingers. So how are they curling? They are curling like this. You can see. So this is like 12, 9, then 6, 3, 12, 9, 6, 3. So that is anti-clockwise direction. So the field will be shown by arrows in anti-clockwise direction. You can try, suppose the current is down. You can try that. Then you can see they are going like this, the curling is going like this. So which direction is that? Clockwise. So you have to make some practice. Okay, so we are saying if the direction of the current towards you, you can see now the way it is. You can see. That is what we call Fleming right hand grip rule. Ukishikilia wire in such a way your thumb points in the direction of current, then your four fingers, as they make the grip on the conductor, they will show you the direction of the field. So I can give you current, I ask you direction of field. The opposite is also true. I can give you the direction of magnetic field, you show me the direction of current on the figure, on the diagram. That is the question you can get. You can also get define Fleming right hand grip rule. Fleming right hand grip rule. Remember, if the finger is in the direction of current, then the curling fingers point in the direction of the magnetic field. So let us make another step to the second. That was magnetic field patterns formed by a straight current carrying conductor. Straight current carrying conductor. A straight one. Okay? That was the issue. We are not showing the rest of the diagram. That. Okay? The current was coming like that. You can now do the opposite. From top down. Then current flows. Top down. Now, I want us to look at current carrying conductor in a loop. See? A loop. So we have something like that. And down here is where you connect your cell. The cell will be connected somewhere here. So at one point, the current goes like this to the left, comes to the right, downwards. So from the cell here, current goes from the left side, it goes upward. Then as it faces the second hole, the current goes downwards. So this is what we call a loop. This is what we call a loop. This one. That way. Okay? Remember? A loop, visualize, is just a wire which has made a hole one side, then it goes through the hole on the right hand side. That is different from a straight conductor. This is a straight conductor, just one. Just one. These ends are connected to the cell. These are connected to the cell. And then now we are talking about a loop. You can see a loop. So what happens, folks, when we sprinkle ion filings here? If we sprinkle ion filings here, remember we don't have a magnet. The key thing, this wire is showing us it is behaving like a magnet. How? By the current in the conductor affecting the ion filings. We don't have a magnet. We don't. But when we allow current to flow in a conductor, it affects the patterns of ion filings. Hence the topic, magnetic effect of electric current. So we've done that with the compass, remember? Today we've done with a straight conductor, and now I'm doing it with a loop. This is a loop, okay? The ion filings will be sprinkled here. So what observation will you make? What observation will you make? That is what we are doing. Magnetic field patterns of a circular current carrying conductor. Okay? What observation will you make? Observation. Observation is what you see, smell, taste, those using senses. So patterns are formed by the ion filings. What you will see, patterns will be formed. Okay? Now, the magnetic compass can help you to trace these patterns as well, the way we started. So, the ion filing patterns are also some kind of circles with hole as radius. With a hole as radius. Okay? With a hole as radius. This as the center of the circle, so you will see patterns round this. Round. We will also see some patterns round. Round. And then towards the center, you may not complete those circles. Okay? You may not complete those circles. So, I want us to understand better so that I can draw for you. Okay? I will draw for you just in a brief moment. Okay, in a brief moment, here you are. I have them here. Something like that. See? You can see the current is up through this conductor, this loop, and then current is going down here. Again, we start up, and then this one down. So what happened? For this, you hold like this. Current is up. For this one, you will hold it downward. So if I may put it the right way, A and B. So A, we are holding like that. This way, it is anti-clockwise. So the pattern will be like that. So if you try, folks, try and see. For this, the current is up. Okay? So we have concentric circles. The field will be anti-clockwise. It's like 12, 9, 6, 3, 12, 9, 6, 3. You can see those numbers are anti-clockwise. And this is downward. So it's like I have 12, I come to 3, 3, 6, 6, 9, 12. See, that is clockwise, okay? From 12, it comes to 3, 3 to 6, 6 to 9, 9 to 12. So you must have that idea. And folks, when you have those two in your mind, you are very far. You are beginning to understand the magnetic effect. Remember, we do not have a magnet that we can see, that this is a magnet, this is a magnet. We don't have. Instead, we are making observation which leads us to the conclusion that this is magnetic effect. Even though we don't have a magnet the way you know it, a bar magnet. But by current flowing in a conductor results into ion filings forming patterns. You may use also the compass to show you the patterns. Now, that observation that we make is what leads us to this heading, magnetic effect of electric current. That when you have electric current, you have some magnetic effects. Okay? Lastly, I want you to look at a solenoid. Okay? A solenoid. A solenoid. A solenoid is just simple wires which are coiled in a particular design. A solenoid. Okay? A solenoid in a particular design. So you have a solenoid here. This is a solenoid. You can see these, they are coils and then coming down. So this is basically a solenoid. And then we shall have what? We shall have the cell here. So this end connected to the cell and this one connected to the cell. So let me just make my solenoid a bit bigger so that you see it better. I can have just 2 or 3 turns. 2 or 3 turns. Not turns, tani, kumi, tani, shirini, turns. The windings. Okay? There. So current comes, goes round, goes round, goes round. Now when current goes round in this conductor, it behaves like a magnet. And for any magnet, you must have magnetic field. So if there is current flowing in a solenoid, this, just wires made in turns. You can take maybe, if you have a long wire, you can take maybe something like felt pen, and then you make it go round. So you will have a solenoid. You met this when you are doing magnetism. Okay? You can have a solenoid and put a nail inside a solenoid. Then you can make the nail a magnet when DC flows. When direct current flows, you will have a nail becoming a magnet. In other words, the nail become magnetized. So we have this. If you have this, you should also know how to draw patterns, because if you sprinkle this, if you sprinkle on a piece of paper, if you have now on a piece of paper, young people, there, I have a solenoid. See, if I have this and I sprinkle here, okay, so this should be going in and out. in and out, you make many. It goes, it comes, then the way it is, you make many holes so that it rests. This rests on a piece of paper nicely. If I could make it, it would be better, but time. So you just make holes. It goes in, it comes out like that. You can make this. So if you sprinkle, you will find patterns now. You will find very good patterns. Very good patterns. Let me try to draw. You will find very good patterns. So that is a solenoid. That is a solenoid. Okay? This is a solenoid. That. So the patterns will be like that. I'm doing like that with broken line to show you the difference between. See? Those will be the patterns now. Okay? So we are going to learn how do you know these patterns. Okay? Let us write. If the coil carrying current is at the right hand, is held in the right hand such that the fingers encircle the loop while pointing in the direction of current flow, the thumb points in the direction of North Pole. So again, what we are saying is this. If I can get another piece of paper, it will be good for me. Let me see there. Okay, so here, just 1 minute. So that is the example of my coil. So if the current is going like that, okay, you can see this is what we are talking about. So it is on your, these are the fingers, the way the coil curves. So this, then the thumb will point in the direction of north. The thumb will point now in the direction of north. If you imagine the coil, my coil has fallen very far here, this. So this, for example, this is the, now if the current is pointing down here and down here, so if it is pointing down, okay, down, for example, this is arrow down. So if these fingers in the direction of the current, then the thumb will point in the direction of north. Remember, the field lines are drawn like that. They come in like that. So some like this. And the lines of force do not meet, boys. They do not meet. So if you hold with your right hand fingers in the direction of the current, then the thumb will point in the direction of north. So this thing requires you to go slowly and understand, don't cram. Go read the book, get some help from the clip, subscribe, tell your neighbors, don't study alone. Till then, bye-bye.